They're a little wet, and I go, dude, pour it down right. I'm sorry. That's all he said.
Easier than that. Come on.
Yeah.
All right, we've made it this far.
I mean, I can turn it.
It took like 15 minutes, so we'll see how it goes today. The Wednesday is gone. It wouldn't save it. I even put something on the Apple QuickTime help, and I got no help. So then this morning I just did like a little, I just clicked some stuff for like a minute and made sure it would work. It worked. Do you remember on Wednesday something glitched? I think that's what screwed it up. So pray for no glitches. Okay. Oh, it's over here. I'm like looking for that. I had to click it all on there and one of my other places. Okay. How many we got? 26. Do y'all need your, everybody knows. All right, we up to 23? Okie dokie. Oh my gosh. Really? Can I be sad?
Yes. We are.
I can move it around. Okay, it's A. Why is it A? You see that the basic connectivity is the same. The only thing that's different is this group is at the top and the H is on the bottom. Okay, in the right structure. It's the only thing that's different. Okay, so they're differing in how they look in 3D space. Okay. My gosh. Okay. Okay, I'm so excited we get to start chapter 2. Okay, have you heard of this guy, Arrhenius? Okay, Arrhenius came up with our oldest definition of acids and bases. And I'm going to kind of go through it kind of quick because I'm praying that you've all discussed this. Acids are substances that dissociate in water to give an H+ ion. Okay? And what are bases? Bases are substances that dissociate and give you an OH- or a hydroxide ion. Okay? Okay, remember that. Just had to get told to start. Okay. If you just pull hydrogen off the periodic table, okay, how many protons does it have? How many? One. One proton. How many neutrons does it have? Zero for the most common isotope. 0, right? Doesn't have any neutrons. Okay. How many electrons does it have? 1. Okay. So what is H+?
2 protons.
2 protons?
It's missing an electron.
You can't. If you have 2 protons, what are you?
Helium.
Helium. Aha. Okay, remember protons give elements their identity. What is the thing that you can lose and gain? Electrons. Okay, so H plus only has one proton. It doesn't have any neutrons. It doesn't have any electrons. Okay, so a lot of times when we see H plus, we refer to it as a proton because that's all that it is. Okay, can you be H minus? What do you think? Have you heard of hydride? Sodium hydride, lithium hydride, potassium hydride, calcium hydride. Surely you've heard of one of those. Okay. All right. So you have how many protons? One. No, only one. If you have two protons, you're helium. Okay. You can only have one. Okay. Now how many electrons you have? Two. And notice that that fills that 1s orbital. Okay. So there's hydride, there's hydrogen, and then there's H plus, which we usually refer to as a proton. So you will hear me say proton for H plus. Okay, which is why I'm going over it. All right, bases just give you hydroxide ion, and that's the Arrhenius definition. That was the original definition. All right. So here are Arrhenius acids. Have you heard of these? Okay, when you dissolve all of them in water, they give up H plus. Okay? Not a one of them is organic on that list. All right, so here's some Arrhenius bases. NaOH, KOH, lithium hydroxide, ammonium hydroxide, magnesium hydroxide. Do you see that they're all things that you probably heard of, right? Okay, probably if I say name an acid, you'll say HCl, hydrochloric. That's like the first one everybody learns. Okay, if I say name a base, you'll say nothing. You're gonna make me sad. Can you not say sodium hydroxide?
Sodium hydroxide.
Thank you. Okay, you know that's a base, right? Stick with the, I'm positive HCl is an acid and NaOH is a base. You can use that to figure out all the other definitions. So if you have a piece of knowledge like that that you're real positive on, be positive. Be like a proton. Be positive. Okay, when Arrhenius acids and bases react with each other, the products are always water and a salt. So if you take HCl plus NaOH, you get H2O and NaCl. Probably the first acid-base reaction you ever saw, right? Okay. Now, you see that little note up there? CH3OH is not an Arrhenius base. Okay? What is different about the structure of CH3OH from the structure of these things over here? Okay, so let me draw it out. Okay, there's two lone pairs on that O for you. There, I'll make it bigger. Okay, so what's different? What can you tell me about these things? Well, especially the first three. This one kind of is a little bit different.
Most of them are metal and non-metal.
Yeah, you got metal ions. There's no metal ion in here, okay? This one, ammonium hydroxide, still has a cation, ammonium and hydroxide, okay? But here, it's all covalent bonds, okay? That's the big difference. People see that OH and they want to make hydroxide ion like so bad they have to write it down, okay? But it doesn't do that, okay? Because right here, that bond is covalent, okay? This is why we came up with other definitions of acids and bases, okay? There were other things that were kind of functioning like acids, or they were reacting with bases, and it was like, wait a minute, that doesn't work with Arrhenius's definition. So we came up with some more. Well, I shouldn't say we. I had absolutely nothing to do with it. It was before my time. Okay, in this one, I want you to identify the Arrhenius acid in the equation below. The whole equation is written out for you. Okay, so what was the Arrhenius definition of an acid? Find it in there. 24, 25. I thought it was, oh, it was 26, wasn't it? Okay. The number left me. Do I have 26? Okay. Yes, it's A. Okay. It's nitric acid. This compound is giving an H plus to this one. Okay? And then here's what you get. Okay, who wanted to pick H3O plus because you learned that hydronium ion is an acid? Okay, that is not the acid. That is what we call the conjugate acid, and we're going to go for that. Okay, I feel your pain. All right, so here is Brønsted-Lowry acid base. Okay, so here's the next definition. Oh, and here's Brønsted. Wait till you see Lowry. Here's Lowry. There they are. They look very smart, don't they? Okay. Acids are proton donors and bases are proton acceptors. Okay? Acids are proton donors. Now, remember what a proton is. Because we go write a little p, what are we going to write? H plus. Okay? Oh, I think I have that on the slide. I used to anyway. I don't know that I bet on anything today. Yeah, there we go. There it is, H plus. Okay? Proton donor, proton acceptor. Okay. Sometimes people get them mixed up. I don't know exactly why, but that happens. Okay, remember HCl? You know HCl is an acid, right? HCl is an acid in the Brønsted-Lowry definition also. Does it donate protons or get protons? It donates them, right? Okay, so they can help you remember. It's like, these are the tricks that I use to get through school. All right, so I've got HCl plus H2O. Okay, who do you think is the acid? HCl. Do you feel pretty confident in that? Because you didn't sound very confident. So I'm just like, okay, all right. So this is the acid. Okay, now do you see that? What is H2O? Water. Okay, water can function as an acid or a base. How do you decide which one it's going to be? By what the other thing is. So if this is an acid, H2O must be functioning as a base. Does that make sense? Okay, so use that logic to figure out the ones that can do both. There's going to be a couple that can do both. All right, let's see what we got. Oh, I'm going to write it all in. Cool. Okay, maybe, if the pen will work. Okay, so what am I going to get? What do you think? When this donates the proton, proton donor, proton donor. Okay, that's donating. Who's accepting it? Water. Where does it go? Yes. So you're going to get H3O. Okay, and then what? Positive. Are you positive?
Yes, ma'am.
Okay. And what else you get?
Chloride ion.
Okay. Down here now, we've got ammonia plus water.
Ammonia is your base.
Ammonia is your what?
Base.
Did you learn that ammonia was a weak base in Jurachem? Okay, good. So what does that tell you water has to be? The acid. Okay. Oh, I think I've got the little arrows. Since I had them on the other one, I bet I do. Okay. We'll talk about the little arrows in a minute. All right, so I've got ammonia plus water. So our base is going to be a proton what? Donor or acceptor? A proton acceptor, okay? Where is it getting the proton from? Water is functioning as an acid, right? I was trying not to give you the end clue. All right, because it was such a tricky question. All right, so what am I going to get on the other side now?
NH4 plus.
Okay.
OH minus.
Okay? Okay, now I'm going to ask you, in the top one up there, I'll go to red, what is the conjugate acid? Okay, conjugate acid comes from the base. Okay, and who is the conjugate base? Chloride. Okay, now we're going to do it on the bottom one. Okay, I got a base and an acid. So who's the conjugate acid? This is like those things that you're like, whoops. Let's put a lot of these on the test, Dr. Rosman. Okay, who's the conjugate base? Yeah, hydroxide ion. Okay, notice that the acid and base are always what's written on the left, and the conjugate is what's written on the right, the product side. Okay, can ammonium and hydroxide ion react to form this? Yes, they can. Okay, and that's why the arrows are written like that. Okay, so it's an equilibrium. If you take ammonia and water, you're going to have all four of these species present at the same time. Okay, you're going to get all of that. And you maybe did things with equilibrium constants back in the day. Yeah, well, we're not doing those.
I have a question.
Yeah.
So on the homework, it had a question about the arrows, and there was a half arrow like it is on the top there, or there was the full length arrows. What's the difference between those, and why, if they both go each way, is there only a half arrow on these?
Oh, you mean like they wrote it, I think I'm getting you. They wrote it like this?
They wrote it like that, yes.
It doesn't matter. It's either or. There's no special thing. Why? Were they picky about it?
Yes.
What you
They were
can't...
super picky about it.
I didn't notice that. Like, you can't do this.
No, it was, you had to pick which direction the arrows were going based off of what the reaction was. And
Okay, we're going to get to the which direction. Notice on this one, the bottom one is bigger.
Yeah.
On this one, the top one is bigger.
Okay.
Okay, how do you know which one is bigger? We're going to get there.
Okay,
So maybe it had to do with bigger, smaller, not double or single-headed. That doesn't matter.
Okay.
That's kind of weird.
I was just really confused on it.
Well, that's why it wasn't due. And I realized they were still in there. Is this the one we just did? Do I have it in twice?
Yeah.
With the words?
we don't
Is that why you knew the answer?
No.
Oh, okay.
No, the words are not there.
we don't have
Okay. But we wrote the words down. Don't ask me. We'll keep going. We'll keep going. All right. Identify the Brønsted-Lowry base. Maybe I was supposed to pull that one out and I didn't. And you'll see in these questions, I didn't put the double arrows at all. I just put the one arrow. Okay, it's 26, right? Who's got the hiccups? Guys, hiccups? I had the hiccups early. Okay, yeah, the B. That is the compound that is accepting the proton, okay? It's CH3NH2, that I can't say what it's called yet. Okay, so the way you decide if the arrows go to the left or right all has to do with pKa, pH, and acidity. Okay, remember that pKa is the negative log of the Ka, and Ka is the acid dissociation constant. And you write the little thing, this times this over this concentration times this, all that, okay? Now, what you need to remember from all that, from back in the day, is the smaller the pKa, the stronger the acid. That's what you got to remember. Okay? And the lower the pH, the more acidic the solution. Okay? Did you learn that the pH scale goes from what to what? What did you learn about pH? 0 to 14. Did you learn about how it can go lower than 0? Yeah. You will see that in this class. It goes lower than those are super acids. Really good acids. Let's just go with that. Okay? And the lower the pH, the more acidic. What is 7? Supposedly neutral. Okay. So if your acid has a pKa less than 1, it's very strong. 1 to 3 is moderately. 3 to 5 is weak. Very weak is 5 to 15. And if you're over 15, you're extremely weak acid. That doesn't mean you can't function as an acid. It just means you're extremely weak. So you have to have a strong enough base to overcome the fact that you're really weak. Okay? Okay? So this is like we're not going to calculate pKa's. You might look them up. Okay? Like in your book or something. They'll probably be, then I'm going to show you things with tables that are going to have pKa numbers on them. You don't have to learn a single pKa. What you need to know is who is more acidic than who. Okay? And the pKa's can help you figure that out if you don't know it. Okay? The most common organic acids are referred to as carboxylic acids. Sometimes they're just called organic acid, but they're typically called carboxylic acid. They have this special group, COOH or CO2H. I showed you that group when we were doing the how to make condensed formulas. Okay? So this is an organic acid. Okay? Remember that the CO2H means this. Get over there. Okay? Means that. All right, just hang on. Let me see what else is on this. Oh, it didn't go back to the pointy thing. Okay, there it is. It's the one that I just drew over there. And this is referred to as acetic acid. Okay, this is the one that you might have learned as HC2H3O2. This H, okay, is this one. That H is that one. These are not acidic. Why do you think a CH would not be acidic and an OH would be acidic? What's different about those two bonds? CH bonds are very nonpolar and OH bonds are very polar. If you're a hydrogen bonded to an oxygen or a nitrogen or sulfur for that matter, you can be really acidic. Okay? So HCl. HCl, that's a nice superpolar bond. That's why it's a strong acid. Okay? All right, hang on. I think I got something else for you. The pKa is 4.76. So where does that fit in that table I gave you on the last slide? Isn't it like weak? All right. Here's another one. This one is called formic acid. Its pKa is 3.75. Is formic acid more acidic than acetic acid? Yes. Does that make sense? Okay. Just from looking at the pKa's, you might not have known that before. That's okay. Okay, here are alcohols. Alcohols contain an OH group. The OH group is referred to as an hydroxyl group. I should have said the other thing was called a carboxyl, but we're going to do it again, so it's okay. Okay, alcohols also have an OH polar bond, don't they? Okay, this is the hydrogen that's acidic, not these. These aren't acidic. None of these 5 are acidic.
This is the one that's acidic. Okay, and remember what we said about CO bonds. While they're polar, they are still covalent. And these compounds do not give up OH minus. You don't take this compound, anybody know what this is? I've shown it to you, I think, already. This is ethyl alcohol, the alcohol that you may drink if you are over 21, and you do so in moderation. Don't drink and drive. Okay, that's it. This is wood alcohol. This will cause blindness. Don't drink this one. Okay? All right, so here's ethyl alcohol. If you dissolve ethyl alcohol in water, do you get hydroxide ion and turn it into a base? No. Okay? It's just alcohol mixed with the water. Okay? And the alcohol in every kind of alcoholic beverage, I guess, is the same alcohol. There's no difference between the alcohol in beer, wine, and vodka. You just get more in the vodka. Okay? But there's no difference. Rum is better. Or tequila. There we go. All right. I'm not supposed to educate you on that. All right, now, I want you to see that the pKa is 15.5. Okay, so where does this fit in the realm of strong and weak? Really weak, aren't they? Okay, look at this one. Good old ethyl. 15.9 for ethyl. Okay. Yeah, they're nice and weak. Did I go the wrong page? Okay. In many acids, the acidic proton is bonded to an oxygen. Okay, here's your alcohol. See that R? We haven't talked about R yet. We're about to talk about R here shortly. Okay, R just means a carbon-hydrogen group. It's like general. This is general. Okay, and so we use that R to just stand for lots of things. Okay, because I could write on the board and write alcohols for the rest of the period. Okay, my arm would fall off and you'd be bored to tears more than you are already. But there's so many alcohols and they all exist, probably. Okay, I suppose I could come up with one that wouldn't. Okay, here's water. Do you see how they're related to water? See how water has that OH? Okay, all that's different is the R is now a carbon-hydrogen group. Oh, here's pKa. Here's a little table. Okay, look at what water's pKa is. Remember, a negative log of the Ka. We're losing a proton off the water. Okay, we're losing a proton off the CH3OH. We're losing a proton. Oh, I said methyl alcohol, didn't I? All right, ethyl alcohol. This one down here that's 17, bless you, that is isopropyl alcohol. That is rubbing alcohol. Okay, so you're probably kind of familiar with these two. I don't know about this one. Okay, and this one is T-butyl alcohol. Okay, notice what they all have in common. They have that H attached to an O. And look what happens as we change what's attached to the O, and it gets bigger and bigger. What happens to the pKa? It gets bigger. So what does that mean about the acidity? It gets weaker. Good. Okay? So water is the best acid that's up there right now. Okay? And you probably don't even think of water as being a very good acid because it isn't. Okay? What have I got? Another? Okay. Electronegative substituents can increase the acidity of alcohols by drawing electron density away from the OH group. So remember that the bond that is important is this bond right here. And I'll just do that, meaning it's attached to other stuff. Okay? So if I'm grabbing electron density and pulling it away, for a base to reach in and pull off that proton, it's a whole lot easier because The electron density is being pulled away because of something electronegative. Can you name me something on the periodic table that's electronegative? Fluorine. Okay, good. You have chemical knowledge. All right, so here is, can you tell me what that is? Carbon is black, red is O, and these are the hydrogens. This is ethanol. Okay, ethyl alcohol. CH3CH2OH. It has a pKa of 16. Okay, that was on the other slide too. All right, now look what I did. I found another picture. But I took these 3 hydrogens and I replaced them with this. These happen to be fluorines. Okay, this poor little picture looks pretty sad on here. All right, CF3CH2OH. So fluorine is very electronegative, right? So what is it going to do to the electron density? It's going to pull it towards it, okay? So what does that do to the acidity of that hydrogen? What do you think? Is it more acidic or less acidic? More. Okay, now I want you to guess a number. What do you think the pKa is for that? Just guess. Like, I want to know where you're thinking. How much do you think that's going to affect it? 2. Okay, what else? 10. Okay. That's it? You're the only 2 who are going to be brave enough to vote? 5. Okay. All right, let's see what we get. I got 3.
Oh gosh.
Not as much as you thought, maybe, but it still went down by 5. Okay, that's pretty good. Okay, so now you can start thinking about, so if I said which is more acidic, this compound or this compound, you could confidently say this compound because I said this or this. No, ethanol or the one with the fluorines. The one with the fluorines. Does that make sense? What if I put 2 more fluorines here? Do you think that would make it more acidic or less acidic? Yeah, good. Okay. Oh, here's a picture of it. Okay, so in this picture, we're using the funky arrows with the pluses. They look kind of light. Are they light? Can you see them? Okay, to show that we're pulling electron density away. Okay, that's all that's showing. Okay, this effect occurs through the bonds of the molecule. It is referred to as an inductive effect. We'll use that word a lot, inductive effect, through the bonds. Okay, that's how electronegativity works, through the bonds. Okay, it's kind of like, I don't know what it's kind of like. Okay, inductive effects arise because of polarization in the bonds between the atoms. Okay, and we put fluorine on there and it's uber electronegative, so it's pulling the electron density towards it. Okay? All right, here is pictures. All right, here's plain old ethanol. Now, do you remember what the red was and what the blue was in these pictures? Red is more electron density, blue is less. Okay, so look what happens when we put the fluorine on. See how it changes? This got even darker, and the red got smeared back over towards the fluorines. Okay, over here, there's not really any red. Okay, so that's why we use these to show you that. Okay? Okay, why is a carboxylic acid more acidic than an alcohol? These 2 things are kind of similar, aren't they? Okay, here's the pKa of acetic acid, and here's the pKa of ethyl alcohol. Well, the carbon, I think I have a little arrow, yeah, right here is bonded to 2 oxygens, and the carbon over here is only bonded to 1. Okay, so what kind of effect is that going to be? Inductive, right? Okay. So you get the inductive effect of the extra oxygen. But heck, we had 3 fluorines on that other one, and it only went down by 5, right? We're going down by 11. Okay, so there's something else involved. This is the conjugate base of acetic acid. Do you see how I got that? So here's our acid, here's our conjugate base. So what did I remove from this? The proton, the H+, okay? Doesn't matter who took it, this is still always the conjugate base, okay? All right, so what can you tell me about that? Anybody see something about it? What do we got here? And over here we got a, and over here we got a, okay. So can't I do that? What is that called? Delocalization of electrons? Resonance. Okay, this conjugate base is stabilized by resonance. Okay? And so because of that, that's why they're more acidic, because resonance effects are stronger than inductive effects, like a ton. If there's resonance, that's like, oh my gosh, super stable. Okay? Everybody got that? Are you still writing? Okay? So that's why these are called carboxylic acids, and these are only called alcohols. They're not alcohol acids, okay? They can function as an acid, but you have to have a really strong base to work with if you want them to be an acid. All right, let's see what's on the next slide. Okay, so curved arrows and reactions. We are going to use curved arrows not only to show resonance, which is what we've done so far, but we're going to use them to show the movement of electrons in a reaction, and we're going to do acid-base reaction. That's it, just acid-base. Okay? A double-headed arrow means the movement of a pair of electrons. We'll do other reactions later. All right, so here's AB. Just random. B is not boron. Okay? So if I'm going to draw an arrow to show the movement of these electrons, where did the electrons in the blue bond go? To B. Okay? How do you know that? Because you look at the products and figure it out. They're just generic. Okay? We'll talk about how you know when there are real atoms there. Okay? Don't fade on me on that. Okay? So here's acetic acid. Okay? Acetic acid. All right. And when it dissociates, what bond breaks? When you dissolve it in water, you're going to break one of those bonds. Which one? The hydrogen to the oxygen, not the hydrogen to the carbon. Okay? The red bond. They won't be color-coded on the test.
Good, I'm colorblind.
Ah! Well, it's a good thing they won't be color-coded on the test. All right, so to show the arrow, I'm going from the bond to the O. Now, why aren't I going from the bond to the H? Who's more electronegative, O or H?
Oxygen.
Oxygen, okay? So what do I get? I get my acetate anion, my conjugate base, and then I get H+. Okay? Now, if I'm going to show it actually reacting with a base like hydroxide ion, okay, so does it matter if I use sodium hydroxide, lithium hydroxide, potassium hydroxide, ammonium hydroxide? It doesn't matter, does it? Because what are those cations? Have you heard the term spectator ions? Okay, so when somebody writes NaOH, you've got to think, oh, the sodium is just hanging out. He just came to the party, he's sitting by the wall. He's not doing anything, not dancing, okay? The hydroxide ion gets to dance, okay? So, that hydroxide ion, one of those pairs of electrons reaches out and picks off the H+. And then what happens to the electrons in the blue bond? This is blue, Taylor. In the OH bond, that's blue. They go to the O. Okay? You can't just have the electrons go to the H, because that H would have two bonds. Does hydrogen ever get two bonds? No. Okay? So you have to break a bond. Okay? This is why hydroxide doesn't take a proton off over here. Okay? Okay, so what do we get? We get acetate anion, just like we got before, and then we get water. Okay? Bless you. Okay. Now, anybody thinking, yeah, the H moved from here to here. But that is not how we draw the arrows. The arrows are drawn to show movement of electrons. That's the rules that the previous people in organic chemistry came up with, not me. Okay, that's their rules. Arrows mean movement of electrons. You may be thinking the hydrogen is going over there, but we don't draw an arrow showing the hydrogen moving. Arrows mean movement of electrons, and I'll remind you that about 1,000 times. All right. Here is acetic acid, and here is hydronium ion. You can actually do this reaction, okay? Even though this is typically considered an acid, and this is considered an acid, okay? So what we're going to do is one of the lone pairs on that O are going to reach out and grab a proton from the hydronium ion, and what happens to the electrons in that OH bond? They go to the O. So don't forget to follow through, okay? Otherwise your ball doesn't make it over the net. Your electrons don't make it over the net. All right, so now what do we get? Do you see how I made a bond with that pair of electrons is in this bond, right there? Okay, and then what else did I get from this part? I got H2O, right? H2O. Okay, so the electrons that were in this bond are now that lone pair. Okay, so when we're drawing arrows for, and this would be like a piece of a big reaction, but acid-base is like almost everything. Okay, and a lot of times you just start with acid-base. But when you draw those arrows, you have to account for where all the electrons are going. Okay, notice we didn't draw any arrows down here or over there. They didn't get to party. Okay, not everybody does something every time. Okay, which reactant is the Brønsted-Lowry base in that reaction? So who is accepting the proton? Right, this guy. Okay, he's our Brønsted-Lowry base. Okay, that makes sense. How are you going to know if acetic acid is going to function as an acid or a base? Look at what the other thing is. The only time it wouldn't is with H3O+. All right, so look up here. This one is CH3OH, okay, and we've got H3O+, hydronium ion. Okay, so who do you think is going to be the base, and who do you think is going to be the acid? What's your guess?
Hydronium is the acid.
Yes. Can hydronium ever be a base? No. You know why? Because of this. Okay? Because it has a positive charge. If you're positively charged, you're not going to take more positive charge. That just doesn't make sense. Honest, it doesn't. Okay? So that means that this alcohol has to be the base. What specific part of it is going to accept the proton of that structure? The oxygen. And what on the oxygen? The lone pair. Okay? So, where do I draw my arrows? No, I'm not going to start there though. I'm going to start over here where the electron density is. So I'm going to start here and I'm going to go from the lone pair to the H. And then I'm going to take the electrons in that bond and put them on the O.
So,
Huh?
so why does it not? I get why it doesn't go the other way, but can you say why it doesn't?
Because the arrows mean movement of electrons. Because that's what it stands for. It's like the electron is reaching out and plucking the proton. Okay? And then these electrons zoom to the O. Okay? So it's movement of electrons, even though in your mind you're going, yeah, the H is moving. But that's not how we draw the arrows. That's not the convention. Okay? Whoever came up with it, I don't know. All right, now, oh, look what I did. Wow. I didn't remember I had those on there. Okay, now can you tell me, oh, I probably have acid too. Can you tell me what the products are? Can you draw them? I'll just erase them just to make, so you can read it later. Okay, can you tell me what the products are? So what do you think you're going to get? I'll tell you what, I'll try clicking the button first. Okay, what do you think you get? You have a bond. What did we make a bond? From the O to the H. Okay, so draw everything that didn't change. Did the CH3 move? No. Did the H over here move? No. Okay, so draw all that. Okay, and then draw your bond to the H. Okay, and what happens to that O? It is now positive. How do you know it's positive? How do you know it's positive? Well, you do the deal. Okay. How do you know this O is positive?
Oh, because it has 3 bonds.
Yeah, this has 3 bonds. And you go 6 minus 2 minus half of 6. Okay, and then the other thing we got was water. And here's our new little lone pair right there. Okay? Here is a nitrogen compound plus OH minus. Okay? So, what do you think the nitrogen compound is going to function as? An acid or a base? Acid. What makes you pick that? Because what is this? And you know that hydroxide ion is a B positive. I mean negative. No. Sure of yourself. How's that? How's that? All right. So, how am I going to draw my arrows? Where do I start? Where is high electron density? The oxygen that's negative. Okay. Let's see if it's, oh, look at there. So I picked a hydrogen. Does it matter if you pick this hydrogen or that one? No. Does it matter if you pick these 3? Yeah. Okay. Now, where is that it? Is that the only arrow I draw? I'm going to take the electrons in that bond and I'm going to put them on the nitrogen. Okay. Now, can you draw what you get? Before I push any clickies. Okay. Although it's 11:50, so I better be fast. Okay. Did you get that? Okay. And then the other thing is water. So things like alcohols and this NH2 thing that I haven't defined yet are going to function as acids or bases. How you decide is by the other thing that it's reacting with. Because could you react that with hydronium? Yes, you can. Okay? Okay, we didn't get to the arrows. Okay. All right. We'll do that next time. At least we got it to work. I just have to come in a half hour ahead. Y'all have a good weekend. I'll see you on Monday. The bell's on. Yeah, you also tuned in mine a long time ago. Oh.
Okay, just kinda, yeah,
Okay, cool.
and we'll get with him,
Okay, thank you.
cause he hasn't come.
Oh, yeah, there's gonna be everything on there. There's gonna